in the two previous examples, what we have been looking at are those kind of two-class problems, right? We are only classifying rocks into two different categories, either sandstone or shale, right? So, but in practice, there are scenarios that we have to actually um, classify data into multiple or maybe more than two categories, right? So one example is the classification of, say, images, right? We have to separate the images into like different categories, and those categories can be more than two, right? So how to actually solve the classification problems involving more than two categories, right? Uh, One possibility is to actually convert the problem, right? You can convert a multi-class classification problem into a two-class classification problem, right? Suppose you just want to separate class A from class B and C. That's a two-class problem, right? Class A is one class, and class B and C is, you can denote it as, say, class A prime, right? You do this kind of two-class separation first, and then after you have separate the data into A and A prime, then you can sort of do a two-class classification for A prime to separate A prime into B and C, right? That's one of the ways of doing things. Um, and here we're gonna show you how to use a generative approach in which we are gonna explicitly compute the logged posterior, right? But our logged posterior are gonna be computed based upon this kind of assumption that's used for FDA discriminative analysis, right? We're gonna assume that the standard deviation is gonna be the same across all the different classes, and the number of classes we're gonna try to classify is gonna be 10, right? We're gonna separate data into like 10 classes. And what can be the data that we're gonna be looking at, right? We're gonna be looking at handwritten digits, those images of handwritten digits that's stored inside of this MATLAB workspace file called digit.mat. Right? It's a MATLAB file, but we can actually read it into Python by using a NumPy library. But before we actually write the code, let's import the libraries, right? Import NumPy as MP, and then import matplotlib.pyplot as plt. And then this time we're going to import a function from the scipy.io library, right? We're gonna import the function using a different syntax. From scipy.io, import a specific function called load mat. That's a function, right? So the syntax is slightly different from the import syntax, right? We're importing from a library a specific function. So the way for calling this load mat is that we don't have to actually prefix the library path or library name in front of the function name. We can just use this function directly, right? So let's see how to. So we're gonna load this MATLAB file into Python variable called dump, right? And then we're gonna call this function called load mat, right? Load mat digit.mat, right? So because I'm using this particular syntax to import a specific function name into the namespace, so here when I use this particular function, I don't have to prefix it with the scipy.io here, right? Because I'm importing this function name into the namespace directly, right? And I'm using this function only once actually. So if I run this code, let me call this particular file E8. Right. Then I'm gonna get a dictionary. I'm gonna get dictionary with 5 elements inside of it, right? And dump is gonna be the dictionary, right? And this dictionary is gonna contain both the training data and this testing data, and I have to actually separate them into like different matrices, right? Different matrices. So what I'm gonna do is that I'm gonna use capital X to represent the training data. It's gonna be dump. Because it's a dictionary, so I have to use the key value, and the key value is the string x, right? And and then T is going to be the testing data, right? And at this point, I can actually get rid of the dump dictionary, right? Because I've got all my training and testing data into these two matrices, so I don't have to use I don't have to store the dictionary in my workspace anymore. I can just get rid of it. So if I run it, I'm gonna be able to actually see the X and the T, these two matrices, right? It's actually not a matrix, it's actually a three-dimensional array, right? If you have used TensorFlow before, it's a tensor. It's a three-dimensional tensor, right? So how do we actually understand the size, right? How do I actually understand the size? So for the training data X, it's 256 by 500 by 10. So the last dimension is actually the number of classes, the number of categories. We're doing this kind of handwritten digit recognition. So we are going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. That's 10 digits, right? So that's the dimension of the that's the last dimension. And then the next to last dimension, the center dimension, is actually the number of images. So for the training data, we have 500 images, right? And for the testing data, we have 200 images. And the first dimension, 256, actually is actually the pixel number, right? So for every image, it's going to be a two-dimensional image with 16 pixels by 16 pixels in each dimension. So 16 times 16, that's exactly 256. So pretty much we're actually storing the grayscale values at those pixels into like a one-dimensional array, right? So how do we actually visualize this kind of image, right? So suppose we wanna take a look at one of those images in the testing data. So T is gonna equal to capital T, right? We want to get all the pixels, and suppose we want to come up with some kind of random image, say 156 image, and then the first category, right? And then all we have to do is to use the plot command, use the matplotlib to make a plot of it. So, and in order to actually show a two-dimensional image, we use imshow, right? Imshow, and then we have to actually reshape this kind of a one-dimensional vector with 256 elements into a matrix with 16 pixels by 16 pixels. So we have to reshape the T, which is 256 one-dimensional vector, into a two-dimensional matrix with 16 pixels by 16 pixels. We reshape this one-dimensional thing into like a two-dimensional thing, and then we have to assign a grayscale, a CMap, color map. Color map, let's just use gray, right? Because it's a grayscale image. It's not RGB, red, green, and blue images, right? So if we run this code, we'll be able to actually see one example image in the testing dataset, which is actually a handwritten digit of 2, right? It looks like that, right? So this is actually how we actually load the data, right? Load the data. Load both training and testing data. But we are not going to use the testing data for training purposes, right? We're going to use the testing data just for testing purposes, right? So now let's before we do anything, let's try to actually get the dimensions, right? Let's try to get the dimensions of the matrices. So D is going to be the number of pixels, and then M is going to be the number of images, and C is going to equal to T dot shape. C is going to be the number of classes, right? And then let's convert. C is supposed to have a value of 10, right? So C is supposed to have a value of 10, right? But for testing purposes, let's just change the C value to 3 manually, right? We're gonna do a 3-class classification. We're just gonna classify the first 3 digits, 1, 2, and 3 first. See how good the performance of our code actually is, and then we are going to extend it to like to like 10 classes, right? And in order to actually extend to 10 classes, all we have to do is to comment out this particular line, right? Get rid of this line, and then all the remaining code is going to do this kind of 10 class classification, right? And then we are going to have to actually construct this kind of a common covariance matrix, right? And then we have to actually come up with a data structure for storing this common uh, covariance matrix. Let's call it S, right? And then what's going to be the dimension of S, right? So what's going to be our feature? What's gonna be our feature list, right? The feature list is going to be the grayscale values for all 256 pixels, right? So this covariance matrix is going to be what? It's going to be 256 by 256. It's going to be a two-dimensional matrix. Um, let's initialize it to all zeros, right? And then the size of it is going to be d by d, right? D is going to be the number of pixels. That's our common covariance matrix, right? And then what's going to be our averages, right? The averages are going to be different for different classes, right? But the averages are still going to be a 256 vector, right? So let's call our averages mu. Mu is going to be np.zeros, right? We're going to store these averages into a two-dimensional matrix, right? And then the number of rows is going to be d, and then the number of columns is going to be c, right? So if we're doing a 10-class classification problem, then we're going to have 10 columns, and each column is going to have 256 rows corresponding to the average grayscale values for the 256 pixels. Right, that's going to be our mu matrix. So now let's try to MLE training. Let's try to compute our compute those values, right? Compute those values from the training data. I mean, right? So we're gonna do a for loop. For y in, we're gonna loop through all the different classes, right? We're gonna loop through, and for each of the class, we're gonna construct one column of the average vector, right? The mean vector. The mu for each column of the mu matrix is gonna correspond to the average for the different pixels across all the different images in the training data set. So it's going to be amp.mean, right? And then we are going to have to actually get x, the training data. X is the training data, right? We are not touching the testing data, right? So if we actually fix the category to y, fix the last dimension of x to y, then x is going to be a two-dimensional matrix, right? The first dimension is going to be 256, and then the second dimension is going to be the images, the different images, right? So the first dimension is going to be the pixel, and then the second dimension is going to be image, right? And this mean has to be evaluated across all the different images, right? So for each individual pixel, we want to average across all the different images in the training data set. And in this case, we have to actually specify the average axis to 1, right? We want to access, this is the zeros axis, this is the first axis, right? We want to average across all the different images, right? And then what's going to be my S value, right? S value is going to be this kind of a prior weighted covariance matrix for individual classes, right? But what I can tell you is that this prior is actually identical. It's identical. It's just 1 over c. Why? Because nyi for each different category is exactly the same, right? So we have how many training data? We have 500. We have 500 training images, and then for each image, for each class, it's 50. It's 50 images, right? So the prior is uniform. The prior is uniform. It's what? It's 1 over c, right? It's 1 over c. So S plus equals 2 is going to be the standard deviation or the covariance matrix for individual classes, right? And then weighted by 1 over c, right? Because 1 over c is the same, so all we have to do is to call the MPCOV x, right? And then divided by c, right? Yeah, the default covariance matrix is gonna. We don't really have to specify any kind of optional inputs for the covariance matrix here because it's actually intelligent enough to actually know how to actually compute the covariance matrix. So this amp.cov is gonna return a matrix that's 256 by 256, right? Um, and the reason is because we are specifying the because the x is stored in this particular way. The dimensions of the x array is stored in this particular way. So there's no row var equals to false, right? There's no need for that, right? If we run this code, we're gonna get the covariance matrix. That's the common covariance matrix. That's 256 by 256, right? And then we're gonna get the mu. That's 256 by 3 classes because we set c to 3 here. If we comment out this line of code, then c is gonna be 10. The mu is gonna be 256 by 10, right? But if we look at this particular expression here, we're going to use this particular expression here. We're going to use this one. Right, C prime is a constant. We don't have to actually compute that. Right, when we do comparisons among different classes, C prime is a constant. It doesn't vary with y, the class ID. So all we have to do is to actually compute the stuff that's in the front. Right, and this one is actually identical. Right, ny over n is 1 over c. It's a uniform thing. So this one is also constant across different classes. So all we have to do is to compute these two terms, right? And if we actually pay attention to the expression here, what's actually common is actually the inverse of the sigma of the common sigma times mu y hat. Inverse of a common sigma times mu y hat. The only thing that's different is the stuff that's multiplied in the front, right? So in order to actually reduce the calculation, what we might want to do is to actually pre-compute sigma inverse times mu y hat. Right? Before we actually loop through all the different images in the testing dataset, let's just pre-compute this thing. Right? So we don't have to actually compute this particular term inside of the loop, right? Because inside of the loop, this term, this multiplication is actually the same. Right? So in order to actually save a significant amount of calculation time, we can actually pre-compute them and store them before the loop through the testing dataset, right? So let's try to actually compute this sigma inverse times mu y, right? So how are we going to compute that, right? We're going to call the result as h. H is going to equal to amp dot. Well, first we have to get the inverse of s, right? That's the inverse of s, right? And it's going to be a matrix, right? And then that's the sigma inverse. What we have to do is to actually multiply mu y hat, right? But don't forget mu y hat, as denoted here, is going to be a vector corresponding to the averages, right, for the y's category, right? So here the averages are stored inside of this mu vector, right? It's actually a matrix, right? It's not a vector. It's a matrix with this many columns, right? But multiply this matrix vector multiplication can be converted into matrix multiplication if we account for all the different y's that's stored inside of the different columns of mu. And this matrix multiplication can be carried out by using the dot function, right? So this way we have actually computed this sigma inverse times mu for all the different categories, for all the 10 different categories, right? So if we run this code, h is going to be what? H is going to be 256 times c. 256 times c. C is 3 here for this experiment here, right? And then once we need to actually use this particular term for different categories, all we have to do is to take out the different columns from this H matrix, right? And every column of that H matrix corresponds to sigma inverse times sigma of one particular y, of one particular class, right? So that's our entire training process. That's and we're done with training. So now let's do our testing. Let's do our testing. Before we do our testing loop, let's come up with a matrix. Let's call it a confusion matrix. This confusion matrix is actually quite useful for classifications, right? So confusion matrix is going to be a two-dimensional matrix, and the number of rows equals to the number of class, and the number of columns also equals to the number of class, right? So if my prediction is identical to the manual classification in the training data, then the diagonal corresponding diagonal component of the confusion matrix is going to be increased by 1, right? But if my prediction is different from the manual classification for a certain example, for a certain image, then it's going to go to the off diagonal component, right? And the row number and column number are going to be determined by the true value, the manual classification values, and the wrongly predicted the prediction values, which is actually different from the manual classification, right? So MP confusion MP dot zeros, it's going to be C by C, right? That's going to be our confusion matrix. It's going to record our error rate, right? And now we can actually go through all the different images in the testing data set. So the testing data is what? The testing data is actually a two-dimensional thing, right? So for each category, for each class, we have 200 images. That's so in order to actually iterate through all the different images in the testing data, we have to actually go through a nested, two levels of nested loop, right? So the first level, say, is a class level in range C, right? And then at this point, let's define a miss rate. Do we really need to define a miss rate? Let's forget about the miss rate. For I in range M is going to be the image, right? The number of images for the training data, for the testing data, right? So M is actually the second dimension of the T shape. That's 200, right? So these two nested loops are going to allow us to iterate through all the different images inside of the testing data, right? And the manual pick, the label for the testing data is actually inside of Y. The Y is actually the manual pick, the manual classification, right? So we do have a ground truth to compare with, right? And then we're gonna T is gonna be the image inside of the grayscale image, the grayscale values, right? So that's T is gonna be the flattened 256 pixels grayscale values, right? And then let's use this expression. Let's use this expression to compute the probability for different Y values for the different classes, right? How many classes do we have? We have C classes, right? So how many probabilities or logged probabilities, right? We have C logged probabilities, right? So let's come up with a predicted probabilities, right? That's so this is an array of zeros, right? And the number of elements is going to be C, and then we're going to change the p-values based upon the calculation, based upon using this particular expression, right? And then let's go through all the different classes, right? So for J in range C, we're going to compute the probability using this expression, right? So P, the J's element of P is going to equal to 1. It's going to equal to X here. X is the T value, right? And it's going to be a vector. So we are going to have to actually do a vector matrix multiplication, right? But what's going to be the thing that we are going to multiply, right? It's a sigma inverse times the average vector, right? And the average vector has been stored in this H matrix, right? So all we have to do is to actually extract the correct column from the H matrix. What's going to be the correct column, right? It's the J's column, right? It's a J's column because we are computing the probability for the J's class, right? And that's the first term. That's the first term. And then we have to subtract the second term, which is actually 1/2 times mu transpose. Mu transpose, what's going to be the correct column for the mu matrix, right? It's going to be mu, the J's column, and then dot. And again, exactly the same thing here. It's going to be a correct column, a corresponding column inside of the H matrix, right? It's going to be H J, and then we can divide it by 2, right? You have to sort of account for this divide by 2, right? Subtraction. And that's it, because this logged prior is the same for different classes, right? And that's our probability for the 10 different classes, right? Or natural logged probability for the 10 different for all the different C's, for all the different classes. And that's it. We can close our loop here. We can close our loop. The indentation is important. Don't type the code at the wrong indentation, right? So now we can close our loop. So what's going to be our prediction, right? We have computed the probability or the logged probability for all the different classes. So the prediction is just going to be np.argmax of the p vector, right? So what exactly is the argmax, right? The max function is going to take out the maximum value inside of this logged probability vector, right? Argmax is going to take out the index that's corresponding to the maximum value of the p vector, right? And that index is our prediction, right? So what we have to do is to actually compare this predicted class with y. That's the manual or manual classification rate, right? So if not equal to y, then we have a wrong classification, right? So how do we actually change the confusion matrix, right? We are supposed to actually add 1 to an off-diagonal component, right? But here we don't really have to because one line of code is actually sufficient. So confusion, the horizontal axis is given by y, right? That's the manual classification, right? And then the vertical axis is going to be PRED, right? That's another integer, right? All we have to do is to add 1 to the corresponding confusion matrix, right? And that's pretty much all the code that we need to write, right? So after we have finished sort of this testing loop, all we have to do is to print out the confusion matrix, right? Confusion matrix. Confusion, right? But let's put a new line here, right? And because we don't want to sort of print out this image with every run, let's just get rid of the plotting code. The plotting code is here, right? Let's comment out the plotting code, right? And now let's run this code and see what the confusion matrix actually looks like. So that's our confusion matrix, right? You can sort of see that the diagonal component is very, very big, which means our correct rate is actually very high, right? But there are some misclassifications. So the zeroth column, the zeroth row corresponds to all the manual classification of 1, right? And our prediction has correctly predicted 199 of them, but one of them is predicted as 2. So that's why you have a 1 on the second column of the first row, right? And then for manual classification of 2s, we got 192 correct, and then but 8 of them were wrongly classified as 3, right? So 8 of them is incorrect. And then for all the manual classifications of 3s, we got 2 of them wrong. Our prediction is actually 2, right? Our prediction is 2. It's supposed to be 3, but we classified them as 2, right? We have 2 images classified wrong. So at least for this kind of 3-class example, we are not actually we're doing a pretty good job. We're doing a pretty good job, right? So now let's comment out this this line of code and then run this code as a 10-class classification problem and see what the confusion matrix actually looks like, right? So let's run this code, and that's going to be our confusion matrix, right? And our confusion matrix is gonna look like that, right? And we have a bunch of misclassifications here. We have a bunch of misclassifications here. But what's actually the correct rate, right? What's actually the correct rate? Um, so what's actually the correct rate for the entire testing data, right? The entire testing data involves how many images? 2,000 images, right? Involves 10 times 200, 2,000 images. So all we have to do is to actually count the total number of misses, right? So miss total is going to equal to 0. And then so for every so if prediction is not equal to y, then miss total plus equals to 1, right? Um, and then let's print correct rate. It's gonna be what? It's gonna be miss total divided by m, that's times c, right? And then it's 1 subtract that, right? It's 1 subtract that. So if we want to look at the percentages, right? We can multiply with 100, and then we put a percentage sign behind it, right? And now let's run it and see. Oh, it's so it looks like I computed the miss total incorrectly, right? Miss total, what's gonna be miss total? Miss total is 202, right? And then, am I doing it right? And then I need to use 1 to subtract the miss total, and then times 100, right? Okay, so now it looks like it's 89.9%, almost 90%, right? This parenthesis is actually unnecessary, right? So if I run this code, it's still gonna. Okay, so the total correct rate is 89.9%. 89.9%. It's considering the simplicity of the code, this correct rate is actually pretty high, right? Because we only wrote 54 lines of code and we got a correct rate that's almost close to 90%, right? But this 90% is actually unacceptable if you are using this kind of a code to actually classify the handwritten digits for applications like postal code, zip code, postal zip code classification, that kind of thing. Because this 10% of a miss rate is going to be astonishing. It's going to be too big for practical applications. And later on, once we have an opportunity to use deep neural networks or neural networks, we can actually improve this rate to like 99% or 98%, right? To reduce the miss rate by to like 2% or something. And this is our example for multiple classes for classification using this kind of parametric Gaussian model for classifying multiple classes.